So we'll get started because I know things are running a bit late. My name is Chris White. I work for National Instruments over in the big blue booth over there. And today I'm going to talk about impairment calibration in quadrature systems. So we're going to go over the quadrature system architecture. Why do we actually need calibration in these types of systems? Sources of the impairments that we see as a result of this type of architecture, the actual impairment correction, and then take a look at some performance results. So quadrature architectures have really become ubiquitous in transceiver designs, in radio design, substantially in handset design for a number of reasons. Many of the benefits there are the cheaper design. You get a reduced BOM cost because you've removed a lot of the components that are necessary in some of these multi-stage architectures. You also get more bandwidth with higher resolution based on today's converter technology, and some of these communication standards like WLAN or LTE, some of these OFDM-based standards were actually designed with these types of architectures in mind, and we'll see why that's important in a minute. But ultimately, for those of you that are not familiar, the quadrature architecture is based on a separate I and Q path that are mixed separately and combined up at the RF frequency to provide you a complex RF signal. And so those are the in-phase and quadrature paths as shown on this really simplified block diagram. But as I mentioned, in each of these paths you have a reduced number of components as a comparison to sort of a traditional heterodyne architecture. So the question is, why do we need calibration in these types of systems? And ultimately what it comes down to is because we have these two paths, the I and Q paths, we get imbalances in the gain and phase in each of those paths. And those result in impairments. And we'll talk about exactly what those look like in a second, but from the perspective of the user or the end user of the radio, that ultimately constrains the data throughput capabilities of your design. So for example, think about an 802.11 WLAN signal that's OFDM based. The plots here I've got are EVM per subcarrier on the left, and then a plot of the constellation on the right. This is an 160 megahertz bandwidth 802.11 AC signal. The RMS EVM of this is about minus 37 dB. So, in a traditional design, maybe for a handset, this actually may be good enough. The spec, I think, on AC for this particular signal is at 32 dB, so it's possible that that's okay. But what you see is this V shape in your EVM per subcarrier, and you can also see in the constellation a little bit of phase rotation and maybe some noise on each of those symbols there as a result of these imbalances. So for the sources of impairments, we'll just kind of break down some of what can contribute to each of these impairments. Ideally, you'd have a perfectly orthogonal I and Q signal. And so these two are mixed with the same frequency local oscillator. They're 90 degrees out of phase with each other, and if those are perfectly orthogonal, you'll get just a single tone, no other spectral content at whatever that offset frequency is from your local oscillator that you're generating. Now in reality, there's a bunch of different things that can contribute impairments. And so one of the first ones that we'll take a look at is what's called local oscillator feed through, or LO leakage. You might have seen that in some spec sheets. And so that's actual physical leakage of the local oscillator signal through your modulator that leaks into your RF path. Another source is actually DC components from your digital to analog converters, and those as well can leak through your IQ modulators to create what manifests as this tone at your local oscillator frequency. So the question is really, do we really even care? As I mentioned, some of these OFDM-based specifications have been designed to account for some of these things. And so if you're looking at something like 802.11, they've actually nulled out the center subcarriers, and they don't carry data on those subcarriers for just this reason, because they essentially won't be able to get any data through on those subcarriers. But other applications do care. If you have single carrier modulation, it becomes important. If you're doing any sort of spectral measurements, it does become important because now you have some impairment spurs that show up in your spectrum. The next impairment is sort of a gain matching. So differences in gain between your I and Q paths. This can be a manifestation of differences in individual gain stages, amplifiers in each of those paths. It could be differences in the magnitude response of your filters, gain errors as a result of different power levels of the LO signal itself, or different magnitude responses of the modulator itself. And these manifest as a tone at the negative frequency offset of the tone you're trying to generate from your local oscillator, as you can see in this picture. Another impairment that actually shows up as the same sort of tone at that negative frequency offset as with the gain errors is IQ phase matching. And so this can be a result of any time skew between your traces on your I and Q paths. It can also be a result of differences in the orthogonality between your I and Q paths of your local oscillator. So anything that makes it not quite 90 degrees out of phase, that will manifest in this way. And a big thing is your filter designs. If you have analog filter on both I and Q paths, there can be phase differences in the phase response and group delay of those filters that can affect this parameter here and cause imbalances between that I and Q path. And we'll actually see what that looks like more practically in a minute. So summing these things all up, we have all of those different contributions, and ultimately what we get is this single tone at the middle at our local oscillator frequency and a tone at the negative offset frequency from the tone we're trying to generate. And as you sort of sweep your tones across the bandwidth, what you get are differing images, and we call them these impairments images, for each particular offset. So the phase and gain response for every particular tone offset may vary across the bandwidth. And that becomes pretty important when we're trying to correct for these things. So true correction actually means that we're correcting for those impairments at every one of these frequency offsets. And this is particularly important for these OFDM-based signals where you do have subcarriers all across the bandwidth. And as I mentioned before, those impairments are really a manifestation of relative phase and gain differences between the I and Q path. So we have to make sure that we're correcting for both of them. So we can use digital filters to do some of this, to do this correction. And here we have just a really basic model of what that might look like. This just to implement a filter to correct those. Now, this is a first model that basically says, okay, well, because our impairments are a result of relative differences between I and Q, we can sort of assume that our I path is static, our I path is perfect, and then we will only need to provide corrections to the Q path of our signal itself. So this sort of system actually, this sort of correction filter actually only works if the images that are manifested as impairments are symmetric across the bandwidth. So we saw that in that image when we had all the different tones sweeping across the bandwidth, that our images actually may be different in gain and phase depending on how far or close from our local oscillator frequency we actually are. So this type of a filter doesn't really hold up too well in practical applications. So what we really need is a complex filter, and so we're going to add a cross filter into this scenario that will allow us to correct for sort of asymmetric impairment properties. And this really provides us with sort of the best result there. So this is a type of filter that you can now create, and it's is our pre-distortion filter ultimately, that you're taking your real IQ data and you're passing this through it before you're sending it to your digital to analog converters. So what does that look like when it's actually been corrected? So what I've got on the left is you could call it a single point correction where you're just maybe moving the gain at the center frequency or phase. And then when we've actually applied this quadrature correction on the right. So the raw design itself the RMS EVM performance is about minus 37 dB, but once we've applied that correction, you can see the constellation is much, much tighter. You almost can't even see some of the constellation symbols. And the RMS EVM for this same 160 megahertz AC signal is minus 49 dB as opposed to 37. So we get a 12 dB improvement in RMS EVM. If you look at our EVM per subcarrier, the plot is generally flat across the band. Now, if you'll see at the very top, right and left edges of that bandwidth, you'll see the little uptick there in EVM performance for those particular subcarriers. And as I mentioned before, you can have issues with your group delay response there at the edges of your analog filters. And so this will be a little bit more difficult to correct using your digital filter and can cause some of this type of an effect. So some trade-offs can be made between your digital design and your digital filter and your analog design. And you could potentially push out your analog roll-off frequency and have an easier time correcting it with your digital filter. However, then you have other considerations like, is my spur rejection or out-of-band rejection sufficient for that application? So that's a sort of a trade-off you have to make, best of the combined world in that sense. So just to reiterate, these quadrature designs are really ubiquitous these days in radio architecture design. And unfortunately, they come along with these challenges that manifest as these impairments. And so providing impairment correction techniques that allow you to get rid of these impairments can substantially improve your performance, as we saw around 12 dB in this particular case. And I just want to make it clear, in radio designs, this is important for things like handsets, but increasingly this type of a design is being used in test instrumentation. And this is where this correction becomes very important so that we can be an order of magnitude better in performance than the actual handsets that we're testing, right? So, any questions? All right, thanks.